The first problem is in regards to CPU scheduling. This program will act as a CPU scheduler and handle scheduling 541 simulated processes using these scheduling algorithms: first in, first out, shortest job first without preemption, and priority with preemption. So there is a input file for this project called datafile.txt. It contains 3 different columns. So the first column contains the arrival time, the second column contains CPU burst length, and the third time contains priority for 541 processes. In order to compile the code, you'll run make in the terminal, and this will generate. From there, to run the program, what you'll do is make test. This will output the executable with the input file, and the 3 output files will generate for the CPU scheduling: first in, first out, shortest job first, and priority. Each of the 3 output files will contain statistics on the throughput, CPU utilization, the average waiting time, average response time, average turnaround time, among other things. Is the source.cpp file. So that it contains one function, read data, and it also contains the main function. In this read data function, we open the datafile.txt and we read in from every process in the source file. The first thing that is created in the main function is a vector container of CPU process variable type, and it's called processes. This will hold all 541 processes that are read in. CPU process is a struct, and it is defined in the helper function. So in this helper function, the CPU process struct contains 4 variables: the arrival time integer, the CPU burst length integer, priority integer, and the response time Boolean factor, and it's set to false from the start. Going back to the main function, we call 3 output files and direct all of the cout from each of the scheduling functions to the OF stream, and it's done for first in, first out, shortest job first, and preemptive priority. Going back to the helper function file, the first in, first out scheduling file uses this function in scheduling. Each of the scheduling algorithms utilize the calculations function. This calculates throughput, CPU utilization, average waiting time, turnaround time, response time, and also outputs the number of processes and the elapsed time. The parameters for this function include the number of processes, the total elapsed time that is calculated within each of the scheduling algorithms, total CPU burst time, total waiting time, total response time, total turnaround time. So now let's go over first in, first out scheduling algorithm within our program. Each of the scheduling algorithms have a .cpp and a .h with a corresponding output file that is generated. First thing is done is that we sort based on the arrival time just to make sure everything's good to go. And then we declare our variables, calculate the waiting time, turnaround time, response time, and burst time, and do it for every process within the datafile.txt. And then we call the calculation function, and all of the corresponding averages and the throughput CPU utilization are calculated. This here is the shortest job first scheduling file. One of the key highlights about this is that it sorts the processes based on burst length. And that's how it differs with preemptive, is that preemptive sorts based on priority and SJF sorts based on burst length. The variables are the same between this one in, first out. Idle time is utilized though in shortest job first and preemptive. The overall while loop for this entire file function is that it basically just makes sure that we are working with the correct amount of processes. In shortest job first, we utilize several different buffers. One of the first things that occurs in the while loop is that we are going to account for idle time when the buffer is empty, and that'll be until the next process. So if the ready indices buffer is empty, we update the idle time and the current time. And in this while loop, if the current index is less than the process's size and the shortest job first process buffer based on the current index, that arrival time is less than the current time, we'll push the current index onto the ready indices. And the ready indices buffer is a vector made out of integers. We'll also update the current index in this while loop. Here we are sorting the processes that arrive at the CPU by burst length. On line 48, we create the variable time till next process, which is when the CPU has time till the next process arrives to work on current processes. On line 50, we create a temporary vector of type integer, and we set it to ready indices. It's a temporary list to properly remove indices from the list. So for this overall for loop, we basically will run it while there are processes to work on in the buffer. We run this outside if statement within the for loop while there is time to work on a process. This if statement checks to see if we have worked on a process at all. It'll then calculate the total response time if we have not. Within the remainder of this if statement, we update the current time and we update the number of processes that the function reads. We also update the waiting time, turnaround time. At the bottom, we call the calculations function from the helper function file. Preemptive is the same as SJF, except that for preemptive, we sort based on priority rather than burst length. After running make test with this program, these are the 3 output files that are generated. They're each run on 541 processes, and they have the same elapsed time, throughput, and CPU utilization between the 3 of them. The average waiting time, turnaround time, and response time is what differs between the 3 scheduling algorithms. For first in, first out, and SJF, the waiting time and the response times were similar. And on the other hand, priority had a higher average waiting time than its response time. The highest turnaround time on average was for priority scheduling, preemptive priority was 71, and then it was first in, first out, and then it was SJF. That concludes problem 1.
For problem 2 of the course project, we have the producer-consumer program. The producer-consumer program is based off the assignment in the textbook, and it basically has a number of threads that are produced that will produce a item in the buffer for the consumer to consume. For this program, it'll utilize the threads, mutex variables, and semaphores. The input files are provided being input 2 seconds wait time, input 4 second wait time, and input 6 second wait time. It'll use these files to generate a corresponding output file, output 2 seconds wait time, output 4 seconds wait time, and output 6 seconds wait time. Here's an example of the input 2 seconds wait time text file. 2 seconds with 1 producer and 1 consumer, 2 seconds with 4 producers, 1 consumer, 2 seconds, 16 producers from consumer, and then a variety of other combinations of those. To compile the producer code, you type make in the console. To run the code, you type make test. It'll take a couple minutes to compile since it has to go through all iterations of 2 seconds, all iterations of 4 seconds, and all iterations of 6 seconds. So in the main file in source.cpp, we'll open up the input files to then read into the function. In the for loop, we'll go through each one of the files, verify that it can open it, open a output file for that input file, and get the lines for each of those input files and send them into the function. In the threads.h file, we have global variables for the mutex and semaphore. We also have global variables for starting and stopping the threads. In the runSym function that was called in the main function, it'll ensure that will clear the vector buffer to ensure there's no overlap between function calls and generate and assign the producer, the consumer, and the timer threads. Here we'll generate all the producer threads. Here we'll generate all the consumer threads. And here we generate the timer thread to start and stop the producer and consumer threads, as well as close the producer and close the consumer threads and reset the global variables. When calling a producer function using the thread, it'll have its individual item that it'll produce. And while the threads are to keep running, it'll wait until all threads are generated and ready, and then sleep for a random time between 0 and 5 seconds. There was no clarification in the rubric for how long it was supposed to run. I just arbitrarily labeled it as 5 seconds. Here's a random item for each producer to produce, any number between 0 and 99. And if the producer is able to successfully add the item to the mutex, the vector buffer, it'll say that it can produce that item. Otherwise, it'll say the buffer is full because it won't be able to insert anything. The consumer is the same way. The only difference is it'll remove an item from that vector buffer. And if it says it can't remove it, it'll say it's empty. And if it can, it'll say what it consumed. The removal and insert functions that access the buffer are the critical zones. And it'll lock the buffer, and then for the insert, it'll add the item, and for the remove, it'll remove the item. It'll then, once it's able to determine if it can add or remove its item, it'll notify the next thread and return the item that it was either adding or removing. In the end, the output for 2 seconds looks something like this. With 2 seconds, 1 producer and 1 consumer, it's about 1-to-1 consumption. Here, the consumer just got to it first. For 4 producers and 1 consumer, it's able to fill up the buffer, and the consumer can't keep up. For 16 producers and 1 consumer, there's way too many producers, so the buffer is almost always full. It'll continue this trend. As long as there's a balance for the producers and consumers, there'll be less errors overall. But once there's too many on one side, you'll get a whole bunch of errors. The more consumers there are, the higher the turnaround time will be, but only up to a certain point. This is the problem described in the operating systems concept textbook.